Hello everyone, welcome back to my YouTube channel. So today I'm here to discuss a research paper regarding the subject Theory of Computation. So let's get started with the overview. So we'll be seeing the title, abstract, introduction, methodology, literature review, result, conclusion, and then the references in this presentation. So coming to the title. The title for this presentation will be Optimizing the Representations in Deterministic and Non-Deterministic Finite Automata. So let's get started with the abstract. In the abstract is, in this research, we focus on optimizing the representations of deterministic finite automata, that is DFA, and non-deterministic finite automata, that is the NFA, which are crucial models in the computational theory. These models are widely used for pattern recognition and language processing. Our study investigates how state reduction and optimization techniques can improve the efficiency of these automata in terms of memory usage and processing speed. By comparing the DFA, which follows a single computing path, and NFA, which follows the multiple paths, we found that optimization can significantly reduce the computational complexity. This contribution to the development of more efficient algorithms and systems, particularly in the area like language recognition and system design. So, coming to the introduction, finite automata, both deterministic and non-deterministic, are the key models used in the theoretical computer science for recognizing the patterns and solving the complex problems. DFA is categorized by having a single path for every input, leading to a clear, predictable computation, whereas NFA allows the multiple possible paths, providing the flexibility but increasing the complexity. The efficiency of these models can become a problem when their state space grows exponentially, making them computationally expensive. The aim of our research is to explore the method for reducing the number of states in this automata without sacrificing their functionality. By doing so, we hope they improve their computational efficiency, making them more practical for use in the real world applications such as the language processing, compiler design, and algorithm development. Literature review. Previous studies have looked extensively into the differences between the DFA and NFA, focusing on their computational efficiency and the application in language recognition. Research have shown that the NFA can be exponentially more compact than DFA, but the process of converting an NFA to a DFA often results in a significant increase in the number of states, making it less efficient. Various state minimization techniques have been proposed for DFA, such as merging equivalent states, but there is still a gap in understanding how these techniques can be efficiently applied to both the DFA and NFA. Our research builds on these studies by introducing new methods of state reducing that maintain the automata's performance while optimizing the structure for better efficiency. Methodology. Our research methodology involves comparing the performance of both the DFA and NFA after applying different state reduction techniques. We used primarily approaches state minimization, which involves a merging of equivalent states, and transition merging, which reduces the complexity of the transition between the states. We apply these methods to a range of computational tasks, including the pattern recognition and language processing, and measured key performances indicators such as the time complexity, memory usage, and the automata's ability to handle the increasing input sizes. Data was collected through the simulation tools that allowed us to observe how this automata behaved under various conditions and how much the state reduction improved the overall efficiency. So the result of our research show that significant state reduction is possible in both DFA and NFA, with some notable differences. For NFA, we are able to reduce the number of states by up to 40%, which leads to a marked improvement in processing speed and memory usage. The reduction, however, increased the complexity of the transition, which is a trade-off that needs to be managed depending on the application. For NFA, we achieved an even greater reduction with an average of 60% fewer states, which allowed for the faster computation, especially in the task involving the large data sets or the complex patterns. However, the flexibility of NFA also introduced challenges in maintaining consistent performance. While NFA performed well in certain scenarios, it became harder to predict and manage as input sizes and complexity grew. Overall, we found that the DFA optimizations are more stable and suitable for the real-time applications, while NFA benefits are more for flexibility but at the cost of predictability and consistency. So here is the conclusion. In conclusion, our research shows that the optimizing representation in both deterministic and non-deterministic finite automata can lead to the significant improvements in the computational efficiency. For the deterministic finite automata, reducing the number of states results in the faster processing time and reduced memory usage, making them ideal for the application that require real-time processing and predictability, such as language compilers and protocol variations. Now, non-deterministic finite automata, on the other hand, benefit greatly from state reduction in terms of flexibility and speed, but are less predictable and harder to control in more complex scenarios. This research highlights the importance of selecting the right optimization strategy depending on the intended application. Moving forward, further research could explore hybrid approaches that combine the strength of both DFA and NFA, providing a balanced solution that optimizes the performance without sacrificing the flexibility or consistency. So, the reference used for this presentation is Succinct Representation of Non-Deterministic Finite Automata. So thank you for watching my video. Like and share the video.